Now let's take examples on how to find the coefficient of friction. We will start with two examples on how to find the coefficient of friction for static friction with a static coefficient, and another two examples on coefficient of friction for a kinetic friction. First example will be basic, second one will be with inclined surface for both kinds of friction. Since we are now with the Winter Games Olympics, so let's talk about a sled. Probably you saw the game that's called Skeleton, where people are sliding on a sled down an inclined path to set the best record from start to finish. This sled is with waxed hickory runners resting on a horizontal, dry, snowy surface, as you can see over here. It needs you to calculate the mass of the sled if the maximum force that can be applied to the sled before it starts moving is 46 newtons forward. As we mentioned before, firstly you set your convention. Forward or to the right is positive, upwards is positive as well. We start as usual with the givens and required. So what is given is the applied force 46 newtons forward. The gravitational acceleration is 9.8 meters per second squared, and you have the coefficient of static friction given as 0.06. That is from the table we mentioned before, or usually it would be just given directly to you. And what is required? The mass of the sled. As usual, we start with the free body diagram. We go to the center of the object and we start to analyze what are the forces being applied to that object. We have gravitational force pulling downwards. We have the normal force pulling upward. And we have the applied force pushing to the right. And we have the static friction will be resisting or pushing to the left. Drawing the vector schematic for the forces, you have applied force to the right, static friction force to the left, and the F net is 0 because this sled, as mentioned in the problem, is not moving anywhere. So the total force on the X or the Y axis or on the horizontal and vertical axes is 0. We analyze the forces for the horizontal. F net horizontal equals F applied plus the F static force. And we have for the vertical direction, we have the normal force plus the gravitational force. Now we know that the F net horizontal and F net vertical is 0, so we plug it in as 0. F applied is F applied as given as a value. We have the static friction force, as you remember from last lecture, equals mu static by the normal force. In this case, the static friction force is pushing to the left or backwards, which can be, based on the convention, a minus value or a negative value. That would give you the applied force equals mu static multiplied by the normal force. Same thing for the vertical forces. We have the normal force minus mg, which is replacing the gravitational force. The normal force would equal the mass by the gravitational acceleration. Now, since we know the normal force, from here we can plug it in the equation we got it from the horizontal analysis of forces. The F applied would equal mu static by mass by gravitational acceleration. Since he's asking for the mass of the sled, so the mass can be equal the F applied over mu static multiplied by g. We have F applied as 46, and we have mu static as 0.06, and we have the gravitational acceleration 9.81. If you do the math, the mass will be 80 kilograms. Again, I'm totally against the author for that simple of a number to have it represented in a more advanced scientific way. There is absolutely no need for that. Just write an 80 kilograms so that will not confuse an entry-level student. Let's take an example about the static friction on an inclined surface. We have a 50 kilogram toboggan is on a snowy hill if the hill forms an angle of 20 degrees with the horizon. The toboggan just begins to slide downhill. Calculate the coefficient of static friction for the toboggan on the snow. You set your directional convention. Uphill is positive and upwards is positive. Downhill and downwards are negative. What we're given the mass equals 50 kilograms, theta is 20 degrees. What we need, coefficient of static friction mu s, and we're given as well the g of 9.81, of course. We start with the free body diagram for the object. We have here gravitational force pulling downwards on the xy Cartesian, and we have the parallel gravitational force parallel to the surface of inclination, and we have the gravitational perpendicular force is perpendicular on the surface of inclination. Normal force is perpendicular to surface of inclination. We have a static friction force pulling against the direction of the movement of the object, which is pulling upwards in this case. As we said before, the angle of inclination is equals the angle by trigonometry equals this angle. So you can use it to split the gravitational force components on the x or on the parallel and perpendicular axes to be able to find the gravitational force values. We're given mass equals 50 kilograms, theta equals 20. We need to find the mu s or the static mu. We're given the gravitational acceleration of 9.81 meters per second squared. We do perpendicular forces analysis and we do the parallel forces analysis with reference to the inclined surface. Keep that in mind. Again, as we mentioned before, you can use Cartesian, but we're using perpendicular versus parallel to make life easier in the analysis, and they will land the same final answer. The F net perpendicular equals the normal force plus the gravitational force perpendicular. F net is 0 because we have a static object, and F parallel net is 0 as well. In this case, the normal force equals minus the gravitational force perpendicular. And if we go back to the free body diagram, F gravitation perpendicular would equals F gravitation cosine theta. We know F gravitation is mass by the gravitational acceleration. And since the F gravitation perpendicular component is pulling downwards, that means the sign for the F gravitation perpendicular would be minus. The F normal would equal, in this case, minus the minus mg cosine theta. Because we have minus and we have minus here. So minus of rearranging the equation and minus of the direction of the force. Don't be confused. It's easy. Normal force would equal mg cosine theta. For the parallel forces, we have 0 for the net parallel force equals the gravitational force perpendicular plus the friction static force. We know that the rearrangement of the equation would give you the friction static force equals minus F gravitation parallel in this case. Since we know that the F gravitation parallel component equals minus mg sine theta, so in this case replace this back here. The F static force would equals minus the minus mg sine theta. So the F static force would equal mg sine theta, but the F static force we know that equals mu static by the normal force. We know that the normal force equals the m by g cosine theta. If you eliminate mg on this side with the mg on this side, then you're trying to find the coefficient of static friction to equal sine theta over cosine theta. By trigonometry, sine over cosine is tan theta. So the coefficient of static friction equals 0.36, and there is no units for the coefficient of friction.